Space is beautiful in photographs, nebulae glowing in impossible colors, galaxies spiraling in quiet symmetry, stars scattered like diamonds across deep darkness. From here it looks peaceful, distant, almost gentle. But space isn't gentle. It's vast, indifferent, and profoundly unaware of us. The universe doesn't notice Earth. It doesn't recognize humanity. We exist as a brief arrangement of matter in a cosmos that follows its own rules, calmly and without intention. And within that calmness are phenomena so powerful, so extreme, that our survival depends not on strength or preparation, but simply on distance. Tonight we're exploring the most terrifying things in space, not in a way meant to frighten, but to understand. Not with panic, but with quiet curiosity. These aren't the familiar dangers like asteroids or solar storms. They're deeper forces, cosmic processes so vast and absolute that they unfold without urgency, without malice, without awareness of what they affect. Wandering black holes, gamma-ray bursts that briefly outshine entire galaxies, magnetars with magnetic fields beyond imagination, the great attractor pulling everything towards something we still can't see. Even the idea that the fabric of reality itself might be unstable. These things exist right now, somewhere in the universe, and strangely there's something calming in knowing this, and realizing how small we are, how quiet our corner of the cosmos is, and how much of the universe simply passes us by. So forget the dramatic images, forget the noise. Tonight we'll calmly drift through the darker side of the universe, and let its vastness carry us gently toward sleep. Black holes are terrifying when they're stationary, objects so dense that space-time collapses around them, creating regions where escape is impossible. Cross the event horizon and you're gone, not just killed but erased, information destroyed, existence ended. But at least we know where those black holes are. We can map them, avoid them, plan trajectories that keep us safe. They're dangerous, yes, but they're predictable. They stay where they are, anchored by their position in space, visible through their effects on surrounding matter. Except some of them don't stay where they are. There are black holes wandering through the galaxy. Rogue black holes ejected from their original positions through gravitational interactions, now drifting through interstellar space with no fixed location. And here's the nightmare part. We can't see them coming. Black holes don't emit light. They're literally invisible against the darkness of space. We detect them by their gravitational effects, the way they bend light from background stars, the way they pull on nearby objects. But if a black hole is traveling through empty space, far from any stars or gas clouds, there's nothing for it to interact with, nothing to bend, nothing to pull. It's just there, invisible, moving, potentially heading toward us. Imagine that. An object massive enough to trap light, dense enough to warp space-time, invisible enough to be undetectable, moving through the galaxy at speeds we can barely comprehend. It could be a light year away, 100 light years, or it could be much, much closer, and we wouldn't know until it was almost on top of us. How do black holes become rogue? The most common way is through gravitational interactions in dense stellar environments. When multiple massive stars exist close together in the cores of globular clusters, or in the centers of galaxies, their gravity affects each other. Sometimes during close encounters, One object gets accelerated to high speeds, flung out of the system like a stone from a slingshot. If that object is a black hole, it becomes a wanderer. It leaves its birthplace and travels through the galaxy, carrying its immense gravity with it, an invisible predator moving through the darkness. Another way rogue black holes form is through supernova kicks. When a massive star collapses to form a black hole, if the explosion is asymmetric, more matter ejected in one direction than another, the black hole receives a kick, a push that sends it moving through space. Some of these kicks are violent enough to eject the black hole from its galaxy entirely, sending it into intergalactic space. So we have black holes, potentially millions of them, wandering through the Milky Way. Most are far away, moving through regions of space we'll never visit. But statistically, some must be closer. Some must be moving through our galactic neighborhood, and we have no comprehensive catalog of where they are. What would happen if a rogue black hole passed through our solar system? First, the gravitational disruption. A black hole doesn't need to hit anything to cause catastrophe. Its gravity extends far beyond its event horizon, warping space, pulling on everything nearby. If a rogue black hole passed within a few light years of the Sun, it would perturb the orbits of comets in the Oort cloud, the vast sphere of icy bodies surrounding our solar system. Those comets, disturbed from their stable orbits, would fall toward the inner solar system. Suddenly, instead of the occasional comet visible from Earth, we'd have dozens or hundreds, all heading sunward, many on collision courses with planets. The asteroid belt would be similarly affected, objects knocked loose, trajectories altered, creating a shooting gallery of destruction. But that's if the black hole stays distant. If it came closer, if it passed through the inner solar system, things would be much worse. Planetary orbits would destabilize. Earth's path around the Sun would change, potentially becoming more elliptical, more tilted, less stable. Seasons would shift. The climate would change catastrophically. If the perturbation was severe enough, Earth might be ejected from the solar system entirely, flung into interstellar space as a rogue planet, frozen and lifeless. Or we might be pulled toward the Sun, our orbit decaying, temperatures rising, oceans boiling away as we spiral inward. And if the black hole passed even closer, if Earth came within the black hole's gravitational influence directly, tidal forces would tear the planet apart. Not all at once black holes aren't vacuum cleaners. They don't suck things in. But the differential gravity stronger on the side facing the black hole, weaker on the far side, would stretch Earth like taffy. Mountains would rise and collapse. Oceans would bulge impossibly high. Eventually, the planet would fragment, breaking into pieces that would spiral into the black hole over hours or days. The really terrifying part? We might not see it coming. A black hole moving through empty space is effectively invisible. We'd only detect it when it started affecting things, when comets changed trajectory, when stellar positions shifted slightly due to gravitational lensing, when something gave away its presence. By then, depending on how fast it's moving and how close it is, we might have years to react, or months, or weeks. And what could we do? We can't deflect a black hole. We can't change its trajectory. We can't negotiate with it or defend against it. We could only watch as it approached, calculating its path, hoping it would miss. And if it didn't miss, if the calculations showed Earth was in its path, there would be nothing to do except wait. Watch the sky, feel the gravity increase, see the stars shift. Know that in days or hours everything ends. Some scientists estimate there could be hundreds of millions of rogue black holes in our galaxy. Most are small stellar mass black holes, formed from individual stars, but some might be larger, intermediate mass black holes ejected from galactic centers, and we've only detected a handful. The rest are out there, invisible, moving through the darkness. Statistically, the odds of one passing close to Earth are low. The galaxy is vast, and we're a small target. But low odds isn't the same as impossible. It could happen. It might be happening now, a black hole moving toward us through the void, and we wouldn't know until it was close enough to affect us. That's the horror of rogue black holes. Not that they definitely will hit us, but that they might, and we'd have no warning, no defense, no way to prevent it. Just an invisible object, massive and deadly, wandering through space, and if we're unlucky enough to be in its path, that's the end. No explosion, no warning, just gravitational chaos followed by oblivion. Sleep well knowing that somewhere in the galaxy right now, black holes are moving, traveling through the darkness, invisible, unstoppable, and we have no idea where most of them are. What would you do if we detected one heading our way? Think about it. What could humanity do with that knowledge? Would we try to evacuate? Would we build shelters? Or would we just wait? If you want to understand the true scale of cosmic violence, if you want to grasp how utterly insignificant we are in the face of the universe's destructive capacity, let me tell you about gamma-ray bursts. These are the most energetic events in the universe. Not the most energetic we can imagine, the most energetic that actually occur. In a few seconds, a gamma-ray burst releases more energy than the sun will emit in its entire lifetime. More energy than our star will produce over billions of years, released in the time it takes you to snap your fingers. And that energy is focused, beamed, concentrated into jets that blast through space at nearly the speed of light, carrying radiation so intense that it doesn't just kill, it sterilizes. It erases. It renders entire regions of space uninhabitable for millions of years. Here's how they happen. When certain types of massive stars die, their cores collapse catastrophically. The star implodes, matter falling inward at nearly a quarter of light speed, compressing to densities that exceed atomic nuclei. The core becomes a black hole or neutron star in seconds, and the infalling matter doesn't just stop, it rebounds, creating shock waves that tear back through the star's outer layers. But some of that matter doesn't escape outward. Some of it swirls around the newly formed black hole, heating up, accelerating, forming an accretion disk. And from the poles of this disk, perpendicular to the plane of rotation, jets emerge. Not normal jets, relativistic jets, matter and radiation moving at a significant fraction of light speed, powered by the black hole's rotation and magnetic fields. These jets punch through the collapsing star, emerge from the poles, and blast into space. And when they do, they create gamma-ray bursts, beams of the highest energy radiation in the electromagnetic spectrum, focused like cosmic death rays sweeping through the galaxy. If you're in the path of one of these beams, you don't get a warning. Gamma rays travel at the speed of light. The light that would warn you, the visible light from the exploding star, arrives at exactly the same time as the gamma rays themselves. One moment everything is fine. The next moment you're being irradiated with energies that make nuclear weapons look gentle. What would this do to Earth? Let's say a gamma ray burst occurs somewhere in our galaxy, not close. We'll be generous, maybe a few thousand light years away. Far enough that you'd think we'd be safe. But gamma ray bursts are so energetic that distance doesn't protect you as much as you'd hope. The beam hits Earth. For maybe 10 seconds, maybe 30, we're bathed in gamma radiation from space. The atmosphere absorbs most of it. Gamma rays don't penetrate air easily, but that's not a blessing. That's a curse. Because when gamma rays hit atmospheric molecules, they ionize them. They rip electrons away from atoms, creating a cascade of chemical reactions. Oxygen and nitrogen, the primary components of our atmosphere, get torn apart and recombined into nitrogen oxides compounds that destroy ozone. Within weeks, Earth's ozone layer would be severely depleted, not just thinned, destroyed across large portions of the planet. Maybe half of the ozone layer gone. And ozone is what protects us from the sun's ultraviolet radiation. Suddenly, stepping outside becomes dangerous. UV radiation floods the surface at levels Earth hasn't experienced since before complex life evolved. Plants begin dying. Phytoplankton in the oceans, the base of the marine food chain, organisms that produce a significant fraction of Earth's oxygen start dying en masse. The effects cascade. With the base of the food chain collapsing, everything above it suffers. Fish populations crash. Ecosystems collapse. On land, crops fail. Plants that can't tolerate intense UV radiation wither and die. Food chains collapse there too. And the ozone depletion isn't temporary. It would take years for the ozone layer to recover, years during which Earth's surface is bombarded with UV radiation, years during which ecosystems remain devastated. By the time the atmosphere heals, the damage to the biosphere might be irreversible. This isn't speculation. Scientists believe gamma-ray bursts might be responsible for some of Earth's historical mass extinctions. The Ordovician extinction, roughly 450 million years ago, killed off a significant percentage of marine life. The pattern of extinction shallow water organisms dying while deep water organisms survived is consistent with ozone depletion. Something killed the ozone layer and a gamma-ray burst is one plausible explanation. It could happen again, any time, without warning. Here's the terrifying part. We've detected gamma-ray bursts from across the universe. We see them regularly, multiple times per year, flashes of gamma radiation from distant galaxies. Each one represents a cataclysm, a stellar death, a beam of destruction sweeping through that galaxy. And they're common. Not rare cosmic anomalies, but regular events. The universe produces gamma-ray bursts constantly. We just happen to be fortunate that none have occurred close to us, aimed at us recently. But recently is a relative term. Recently in cosmic terms means millions of years. A gamma-ray burst could have occurred in our galaxy thousands of years ago. The beam aimed away from us, and we'd never know. We'd just see a distant supernova, bright but harmless, unaware of the death ray that missed us. And there are candidates, stars in our galaxy that might produce gamma-ray bursts when they die. Betelgeuse is one, a red supergiant in Orion, visible to the naked eye, massive enough that when it collapses, it might create jets. If it does, if those jets happen to be aimed toward Earth, we're in the beam path. Now, Betelgeuse is far enough, several hundred light years, that even a direct hit might not be catastrophic. The beam would have spread somewhat, diluted over distance. It might cause significant ozone depletion, but perhaps not total collapse. But we don't know. We've never been hit by a gamma-ray burst. We don't know exactly how resilient our atmosphere is. And Betelgeuse is just one candidate. There are others. WR-104, a Wolf-Rayet star, is another potential gamma-ray burst source. This one is closer, and its rotation axis might be pointed toward us, meaning if it goes supernova and produces jets, we're potentially in the line of fire. Might and potentially are the operative words. We don't know which stars will produce gamma-ray bursts. We don't know when they'll explode. We don't know if their jets will be aimed at us. All we know is that these stars will die eventually, and if they die the wrong way, if the jets point the wrong direction, Earth could be in serious trouble. The universe has already fired millions of these cosmic guns. We've been lucky so far, no direct hits, no beams aimed precisely at us from close range. But luck doesn't last forever. Statistically, over billions of years, Earth will eventually be in the path of a gamma-ray burst. Maybe a distant one, weakened by distance, survivable. Maybe a close one, devastating, civilization ending. We won't see it coming. The star might be visible in our sky, might be something we've observed and studied, but we won't know it's about to produce a gamma-ray burst. When it does, the burst travels at light speed. The moment we see the explosion is the moment the gamma rays arrive. No time to react. No time to prepare. No time to do anything except experience the consequences. And here's another nightmare. We might have already been hit, and the burst is still traveling toward us. If a star 1,000 light years away exploded yesterday, aimed a gamma-ray burst at Earth, and those gamma rays are now racing toward us through space, we won't know for 1,000 years. We can't know. The information can't reach us faster than light. So right now, as you read this, a beam of gamma radiation might be crossing the galaxy, moving at light speed, aimed directly at Earth. It might arrive in 1,000 years, 100 years, 10 years, tomorrow. We wouldn't know, couldn't know. The universe keeps its threats secret until the moment they arrive. Gamma-ray bursts are the ultimate cosmic horror. Not because they're malicious, the universe isn't malicious, it's indifferent, but because they're unstoppable, unpredictable, and absolutely devastating. They turn stars into weapons, beaming death across light years. And if you're unlucky enough to be in their path, there's nothing you can do. No defense, no shelter, no escape. Just a flash of gamma radiation you can't see, can't detect, can't avoid. And then consequences, immediate consequences, long-term consequences, consequences that cascade through ecosystems and biospheres and civilizations. The Ordovician extinction might have been caused by a gamma-ray burst. Will the next great extinction be caused by one too? Will ours? We don't know. Can't know. We just have to hope we're not in any beam paths. Hope that the stars capable of producing these bursts either don't aim at us or don't die while we're around to experience it. Hope. That's all we have. Hope and luck and the vast emptiness of space that keeps most threats far away. But space is less empty than it seems, and gamma-ray bursts are more common than we'd like. So we wait, watch the stars, monitor the candidates, and hope that when they finally die, when they collapse and produce their jets and create their bursts, we're not where those beams are pointing. Because if we are, there's nothing we can do. Nothing except watch the sky light up, feel the atmosphere change, and know that something impossibly far away just reached across light years of void and struck us. Not with intention, not with malice, just with indifferent cosmic violence. That's what gamma-ray bursts are. Not evil, just deadly. And we're exposed, always, forever. Should we be monitoring nearby stars more closely? Or would knowing about an incoming burst just give us time to panic before the end? Think about it. What would you want to know? Everything I've described so far, rogue black holes, gamma-ray bursts, these are violent events, explosions, collisions, physical threats moving through space, dangerous but comprehensible, objects that can hurt us, destroy us, end civilization. What I'm about to describe is worse, not because it's more violent, but because it's more fundamental. This isn't a threat to life or civilization. It's a threat to reality itself. Let me explain vacuum decay and why it might be the most terrifying possibility in physics. First, we need to understand what physicists mean by vacuum. Not the absence of air in physics. Vacuum refers to the lowest energy state that space can have. Empty space, devoid of matter and radiation, but not devoid of quantum fields. These fields permeate all of space, and they have energy states. The lowest energy state is called the true vacuum. Any higher energy state is a false vacuum. Here's the problem. We don't know which one we're in. Our universe might be in a true vacuum state, the absolute lowest energy configuration, stable and permanent. Or we might be in a false vacuum, a higher energy state that appears stable but is actually metastable, like a ball balanced on a hillside. Stable for now, but if something disturbs it, if it finds a way to roll downhill to a lower energy state, it will, inevitably, catastrophically. If our universe is in a false vacuum, it could decay into a true vacuum at any moment. And when that happens, reality as we know it ends. Here's how it works. Somewhere in the universe, randomly through quantum tunneling, a tiny bubble of true vacuum appears. This is possible, even without any external cause. Quantum mechanics allows for spontaneous transitions between states. It's probabilistic, rare, but not impossible. This bubble is microscopic at first, smaller than an atom, but it's lower energy than the false vacuum surrounding it, and lower energy states are more stable. So the bubble doesn't collapse, it expands. The boundary of this bubble moves at the speed of light, exactly the speed of light, not slower, not faster. It expands in a perfect sphere, growing larger every second, consuming space as it travels. And everything inside the bubble, gone, not destroyed, transformed. Inside the bubble, the laws of physics are different. The quantum fields that define our reality have different values. Particles that are stable in our vacuum might not exist in the true vacuum. The electromagnetic force might have a different strength. The mass of electrons might be different. Chemistry, as we know, it might not work. Atoms couldn't exist as they do now. Matter would be different. Energy would be different. The very fabric of reality would be rewritten. And this bubble is expanding at the speed of light, which means you can't see it coming. The light that would warn you any signal, any information about the bubble's approach, travels at the same speed as the bubble itself. The warning arrives at exactly the same moment as the destruction. One moment you exist in our universe with our physics, our reality. The next moment, the bubble passes through you, and you're in a different universe with different rules. Except you don't exist anymore, because the particles that made you, the chemistry that sustained you, the physics that allowed you, all of that is gone, replaced by something else. It's not death. Death implies you were alive and then you weren't. This is more fundamental. This is the erasure of the conditions that allowed you to exist in the first place. And here's the truly nightmarish part. This might be happening right now. A bubble of true vacuum could have nucleated somewhere in the universe millions of years ago, billions of light years away. Right now, it's expanding, consuming space, rewriting reality, moving toward us at the speed of light. And we wouldn't know, couldn't know. There's no way to detect it, no way to see it coming, no way to know how close it is. It could be 1 billion light years away, meaning we have 1 billion years before it reaches us. It could be 1 million light years away, meaning we have 1 million years. It could be 100 light years away, close by in cosmic terms, and we'd have a century before reality ends. Or it could be 10 light years away, 1 light year away. Close enough that the bubble will reach us within human lifetimes, within this generation, and there's no way to know. The universe could end tomorrow, today, in the next hour, in the time it takes you to read this sentence. A bubble of true vacuum could pass through Earth, through the solar system, rewriting physics, erasing everything we know, and you'd never see it coming. No warning, no sign, just transition, instant and absolute. This isn't science fiction. This is a serious prediction of quantum field theory. The mathematics works. The mechanism is understood. Whether it will actually happen depends on one question. Are we in a false vacuum or a true vacuum? And we don't know the answer. The calculations are difficult, dependent on precise measurements of particle masses and field strengths. Current data suggests our vacuum might be metastable, not stable, not unstable, but somewhere in between. A state that could last effectively forever, or could decay at any moment, depending on quantum probability. The Higgs boson discovery gave us crucial information about vacuum stability. The Higgs field is one of the quantum fields that permeates space, and its properties affect whether our vacuum is stable. When scientists measured the Higgs boson's mass, they could calculate the vacuum stability. The result? Uncomfortably ambiguous. The measurements suggest we're close to the boundary between stability and instability, close enough that small uncertainties in the data could tip us either way. We might be stable, safe for trillions of years, or we might be metastable, vulnerable to decay at any time. And there's another horrifying possibility. We might be in a long-lived false vacuum that will eventually decay, but not for an incomprehensibly long time. Not millions of years, not billions, trillions of years, quadrillions. Timescales so vast that all the stars will burn out, all the black holes will evaporate, and the universe will be cold and dark long before the vacuum decays. In that scenario, vacuum decay isn't a threat to us. It's a threat to the far future, to a time when nothing exists anyway. But it's still disturbing. It means reality itself has an expiration date. The laws of physics aren't eternal. They're temporary, and eventually they'll be replaced by something else. Everything we know, everything that exists, everything that could ever exist under our physics, all of it is temporary. Not just the matter, not just the structures, but the very rules that allow anything to exist are provisional, borrowed time, waiting for the vacuum to find its true state. Can we prevent vacuum decay? No. Can we detect a bubble before it arrives? No. Can we shield ourselves, escape, survive? No. If vacuum decay happens, if a bubble reaches us, we're done. Not just dead unmade. The physics that allows us to exist would be gone. Some physicists worry that particle accelerators might trigger vacuum decay. By colliding particles at extreme energies, by probing the Higgs field at high intensity, could we accidentally nucleate a bubble? Could an experiment here on Earth create the seed that destroys the universe? Probably not. The energies we reach in accelerators are tiny compared to natural cosmic ray collisions. If particle collisions could trigger vacuum decay, cosmic rays would have done it billions of years ago. The fact that we still exist suggests it's safe, but probably not isn't the same as definitely not. There's a non-zero chance, vanishingly small, but not zero, that the next major particle physics experiment could be the one that triggers vacuum decay. That humanity's attempt to understand the universe could be what ends it. It won't happen. The odds are astronomically low, but they're not zero, and that's unsettling. Every time we probe deeper into fundamental physics, every time we push to higher energies, we're testing the stability of reality itself. And even if we don't trigger it, even if we're perfectly safe in our experiments, vacuum decay could still happen naturally. Quantum tunneling allows transitions between states without external cause. Random chance, probability. Somewhere in the vast universe, a bubble could nucleate spontaneously, and once it starts, it never stops. The only comfort, if you can call it comfort, is that if vacuum decay happens, it's instant and universal. Everyone goes at once, no prolonged suffering, no survivors watching civilization collapse. Just an instantaneous transition from existence to something else, something we can't comprehend because it operates under different physics. You wouldn't feel anything. There wouldn't be time to feel anything. The bubble moves at light speed. Your nerve signals move much slower. The bubble would pass through you faster than your brain could process what's happening. No pain, no fear, no awareness, just transition. Is that better or worse than seeing death coming? I don't know. There's something almost merciful about instant, painless erasure. But there's also something deeply disturbing about the idea that reality itself is temporary, that existence is contingent on the stability of quantum fields we can barely understand. We live in a universe that might be fundamentally unstable. Our existence might depend on nothing more than the fact that quantum tunneling hasn't occurred yet in their own place. We're here not because the universe is safe, but because we've been lucky so far, and luck runs out. Maybe not in our lifetimes. Maybe not for billions of years. Maybe never. Maybe we're in a true vacuum after all, stable and eternal. But maybe not. Maybe the universe is metastable. Maybe the clock is ticking, counting down to the moment when a bubble nucleates and reality begins rewriting itself. And if that happens, we'll never know. The information can't reach us faster than the bubble itself. We'll exist one moment and not exist the next, with no transition, no awareness, no final thoughts. Just nothing. Instant and absolute. That's vacuum decay. Not a threat you can fight or flee from. Not a danger you can prepare for or defend against. just the possibility remote but real that reality itself is temporary and could end at any moment. Sleep well knowing that the universe might be less stable than it appears, that existence might be borrowed time, that everything could end not with a bang or a whimper, but with a bubble of different physics expanding at light speed, rewriting reality, erasing everything, and you'd never see it coming. Does it change how you live knowing this is possible? Or is the remoteness of the threat enough that you can ignore it? What would you do differently if vacuum decay were confirmed to be inevitable? Imagine the strongest magnet you've ever encountered. Maybe a refrigerator magnet. Maybe a powerful neodymium magnet that can pinch your skin if you're not careful. Maybe an industrial electromagnet capable of lifting cars. Now, forget all of that. Those magnets are nothing, toys, barely worth mentioning. There are objects in the universe with magnetic fields so powerful, so incomprehensibly strong, that they warp the very atoms they pass through. Objects that would kill you from the distance of the moon. Objects that could erase the data from every hard drive on Earth from halfway across the solar system. These are magnetars, and they're the most magnetic objects in the known universe. A magnetar is a type of neutron star, the collapsed core of a massive star that died in a supernova. When a star explodes, its core is crushed by gravity to densities that defy comprehension. All that mass, all that matter that used to be spread across millions of kilometers, compressed into a sphere smaller than a city. Neutron stars are already extreme. Matter so dense that a sugar cube-sized piece would weigh as much as all of humanity combined. Gravity so strong that if you fell toward one from a height of just a meter, you'd hit the surface at a significant fraction of light speed. Spin rates so fast that the entire star rotates multiple times per second. But magnetars add another layer of horror: magnetic fields. When a neutron star forms, it inherits the magnetic field from its parent star. But the collapse amplifies that field dramatically. Imagine taking a magnetic field and compressing it along with all the matter, squeezing it into a smaller and smaller volume. The field strength increases, vastly increases. A typical neutron star might have a magnetic field 1 trillion times stronger than Earth's. That's already incomprehensible. But magnetars have fields 1,000 times stronger than that. We're talking about magnetic fields so powerful that they exist at the theoretical limit of what physics allows. What does a magnetic field that's strong do? It warps space. It affects light passing through it, changing the polarization of photons. It tears at atoms, distorting their electron clouds, making normal chemistry impossible. Within the magnetar's field, matter behaves differently than anywhere else in the universe. And if you were close enough to experience it, it would kill you. Horribly. Let's say you're approaching a magnetar from a safe distance, somewhere in orbit around it, protected by your spacecraft. You're far enough away that the magnetic field is merely incredibly strong, rather than instantly lethal. What happens? First, any magnetic materials in your spacecraft would be ripped apart. Steel, iron, anything ferromagnetic would feel forces powerful enough to tear molecules apart. Your ship would need to be made entirely of non-magnetic materials, and even then, the field would induce electrical currents in any conductors. Circuits would short out, electronics would fail. Anything with moving parts would seize as induced currents created opposing magnetic fields. But forget the spacecraft. Let's talk about you. Your body contains iron. In your blood and hemoglobin, iron atoms are essential for carrying oxygen. In a normal magnetic field, even a strong one, this isn't a problem. The iron atoms are bound into molecules, and while they respond slightly to magnetism, the effect is negligible. Not here. In a magnetar's field, even from a distance, the magnetic forces on those iron atoms would be substantial. Your blood would try to align with the magnetic field. The hemoglobin molecules would twist, distort, potentially break apart under the stress. Blood flow would be disrupted. Oxygen transport would fail, and that's from far away. Get closer, and things get much worse. If you somehow descended to the magnetar's surface, which you couldn't, because you'd be dead long before reaching it, the magnetic field would tear your atoms apart. Not figuratively, literally. The field would be strong enough to distort the electron clouds around atomic nuclei, stretching atoms into elongated shapes, making the formation of molecular bonds impossible. You wouldn't just die. You'd cease to be chemistry. Your body would dissolve at the atomic level, electron clouds unable to maintain their shapes, atoms unable to bond, matter reduced to a plasma of disassociated particles. But you don't need to land on the surface for a magnetar to kill you. You could die from the moon's distance. A strong magnetar one with a magnetic field at the upper end of what we've observed would be lethal from roughly the distance between Earth and Moon. That far away, the field would still be intense enough to disrupt cellular processes, to interfere with neural signals, to induce electrical currents in your nervous system strong enough to cause cardiac arrest. You'd die from magnetic field exposure the way you'd die from extreme radiation, your biology simply unable to function in that environment, and there's no shielding that would help. You can't shield against magnetic fields the way you can against radiation. Magnetic fields penetrate matter. They pass through lead, through rock, through anything. The only defense is distance. Now imagine you're not just near a magnetar but experiencing one of its outbursts. Magnetars don't sit quietly. Their magnetic fields are so strong that they stress the neutron star's crust, warping it, twisting it, creating tension. Eventually, that tension releases in what's called a starquake. The crust of the neutron star suddenly shifts, fracturing, relieving the magnetic stress. When this happens, energy is released. Enormous amounts of energy. The magnetic field lines snap and reconnect, accelerating particles to near-light speed, creating bursts of X-rays and gamma rays that blast into space in all directions. These outbursts can be detected across the galaxy. A starquake on a magnetar tens of thousands of light-years away can create a burst bright enough to light up Earth's upper atmosphere, ionizing particles, creating brief auroras, affecting satellites. In December of 2004, a magnetar in our galaxy experienced a massive starquake. The resulting burst of gamma rays and X-rays reached Earth about 50,000 light-years away and was the brightest event from outside our solar system ever recorded. It briefly overwhelmed detectors on multiple satellites. It ionized atoms in Earth's upper atmosphere. For a fraction of a second, a star halfway across the galaxy was visible to our instruments as one of the brightest objects in the sky. And that magnetar was 50,000 light-years away. Imagine if it had been closer. Imagine if a magnetar existed in our stellar neighborhood within a few hundred light-years. A major starquake from that distance would be catastrophic. The burst of high-energy radiation would hit Earth's atmosphere like a gamma-ray burst, ionizing the upper atmosphere, destroying ozone, creating nitrogen oxides. The magnetic pulse might be strong enough to induce currents in power grids, electronics, anything conductive. A global electromagnetic pulse, natural rather than man-made, powerful enough to fry circuits, collapse power grids, disable satellites. The immediate damage might be survivable. Humans can endure radiation in short bursts, and the atmosphere provides shielding. But the long-term consequences would be severe. Ozone depletion, disrupted food chains, technological collapse. And unlike a gamma-ray burst, which happens once and ends, magnetars can experience multiple starquakes. The threat could recur multiple times over years. Fortunately, no known magnetars are close enough to pose an immediate threat. The nearest confirmed magnetar is thousands of light-years away, far enough that even major outbursts are merely detectable rather than dangerous. But here's the unsettling part. We don't know where all the magnetars are. Magnetars are difficult to detect when they're quiet. They're small, dark, emitting very little visible light. We find them primarily through their X-ray emissions and their outbursts. If a magnetar exists nearby, but happens to be in a quiet phase, no recent starquakes, no major activity, we might not know it's there. And magnetars can stay quiet for long periods, years, decades, possibly centuries. During quiet phases, they're nearly invisible, detectable only if we happen to be looking at exactly the right spot with the right instruments. There could be a magnetar relatively close to Earth, within a few hundred light-years, and we might not know. Not until it experiences a starquake, not until it becomes active, not until it releases one of those massive bursts of radiation, and by then it's too late to prepare. The radiation is already on its way, traveling at light speed, arriving just seconds or minutes after the light that lets us see the burst. Even without starquakes, the mere presence of a nearby magnetar would be concerning. The magnetic field extends far beyond the star itself. A magnetar's magnetosphere, the region of space dominated by its magnetic field, can extend thousands of kilometers outward. Anything passing through that region would be subjected to forces no spacecraft is designed to withstand. If a rogue magnetar 1 ejected from its birthplace, wandering through the galaxy passed through our solar system, it wouldn't need to hit anything to cause damage. Its magnetic field would disrupt planetary magnetic fields, affect solar wind patterns, potentially interfere with Earth's magnetosphere in ways we can't predict. The scenarios are speculative, thankfully. Magnetars are rare, and the odds of one wandering close enough to affect us are vanishingly small, but they exist. Somewhere in the galaxy right now there are neutron stars with magnetic fields so strong they warp reality, so powerful they kill from impossible distances, so intense they represent some of the most extreme conditions the universe can create. And occasionally they explode. Not physically, they don't blow apart, but magnetically. Starquakes release bursts of energy that propagate across the galaxy, invisible until they arrive, devastating if you're too close. We're safe for now. We're far from any known magnetars, far enough that even major outbursts are just interesting events to observe rather than existential threats to experience. But the universe is old, and magnetars are long-lived. A magnetar can persist for millions of years, slowly cooling, slowly weakening, but remaining dangerous throughout its existence. And in a galaxy with hundreds of billions of stars, there are likely thousands of magnetars, most of them unknown to us. One of them could be close, closer than we realize. Quiet now, but capable of erupting at any time, releasing a burst of radiation that crosses light years in moments, announcing its presence only by the damage it causes. Magnetars are nature's proof that magnetic fields, something we use for refrigerator magnets and MRI machines, can be weaponized at cosmic scales, that a force we consider mundane and controllable can become powerful enough to tear atoms apart, distort space, kill from planetary distances. They're out there, spinning in the darkness, magnetic field lines twisted and stressed, crusts under tension, waiting for the next starquake, the next release, the next burst of energy that propagates across the galaxy. And we can only hope we're never close enough to experience one, which is scarier: instant death from radiation or slow death from ozone depletion. If a magnetar eruption hit Earth, which would you prefer? Think about it. We're moving. Right now, as you read this, you're not just spinning with Earth's rotation or orbiting with the planet around the sun. You're moving through space on a much grander scale, carried along by the solar system's motion through the galaxy. And the galaxy itself is moving, pulled by gravity toward something massive, something we can't see, something we don't fully understand. This is the great attractor, and it's one of the most unsettling discoveries in modern cosmology. Not because it's violent or deadly in any immediate sense, but because it represents something fundamental about our cosmic situation. We're not in control. We're not stationary. We're being pulled inexorably toward a destination we didn't choose and can't avoid. Here's what we know. When astronomers measure the motion of galaxies, they expect to see expansion. The universe is expanding, space itself is stretching, and galaxies should generally be moving away from each other as they're carried along by this expansion. But when they measured our galaxy's motion, they found something strange. The Milky Way isn't just participating in cosmic expansion. It's also moving in a specific direction, pulled by gravity towards something beyond the normal expansion patterns. And it's not just us. Our entire local group of galaxies, including Andromeda and dozens of smaller galaxies, is moving in the same direction. Something is pulling us, something massive enough to overcome cosmic expansion on local scales, to drag entire galaxy clusters through space, to affect the motion of objects across hundreds of millions of light years. That something is the great attractor. We can't see it directly. It lies in a direction called the zone of avoidance, a region of the sky obscured by the Milky Way's own dust and gas. Our galaxy's disk blocks our view in that direction, creating a band across the sky where distant objects are hidden behind foreground material. And the great attractor sits right behind that obscuration, invisible to optical telescopes, hidden by our own galaxy structure. But we know it's there. We can measure its gravitational effect on surrounding galaxies. We can see how matter moves, how galaxy clusters are being pulled, how the local universe's structure is shaped by this massive concentration of mass. And when we calculate how much mass would be required to create these effects, the numbers are staggering. The great attractor isn't a single object. It's a region of massive concentration of galaxy clusters, dark matter, and gravitational influence occupying a volume of space so large that our entire local group of galaxies is just a tiny satellite being pulled along. It contains the mass of tens of thousands of galaxies, all clustered together, all pulling on everything around them. And we're moving toward it. Not quickly by human standards. The motion is measured in hundreds of kilometers per second, which sounds fast until you realize the distance scales in space are so vast that we won't arrive for billions of years. But we're moving nonetheless, pulled by gravity, unable to resist. There's something deeply unsettling about this. We like to think we're in control, that our motion through space is deterministic, predictable, chosen. But the great attractor proves otherwise. We're passengers. Our galaxy is being dragged through space by forces beyond our control, toward a destination we can't see, on a time scale longer than our species has existed. And it gets stranger. As we've learned more about large-scale structure, we've realized the great attractor itself is being pulled. It's not the final destination. Beyond it, there's something even larger, a massive supercluster called Laniakea, which contains the great attractor and everything around it, all flowing toward another concentration of mass, even farther away. It's gravitational currents, flows. The universe on the largest scales isn't static or simply expanding, it's dynamic, with matter streaming along gravitational rivers, pooling in clusters, being pulled toward the densest regions. We're caught in one of these currents, flowing toward the great attractor, which is itself flowing toward something else. Where does it end? We don't know. The flows extend across hundreds of millions of light years, possibly farther. There might be structures we haven't detected yet, even larger concentrations of mass pulling entire superclusters through space. And we're helpless to resist. Gravity doesn't care about our wishes. It doesn't care if we want to stay where we are. It just pulls relentlessly, moving us through space whether we like it or not. Now, to be clear, this isn't an immediate threat. A great attractor isn't going to destroy us. We won't fall into it in any catastrophic sense. The timescales are too long, and long before we arrive, other factors will become relevant. The Milky Way's eventual collision with Andromeda, the evolution of the Sun, the expansion of space on even larger scales. But that's not what makes it disturbing. What makes it disturbing is the realization of powerlessness. We're being pulled through the cosmos by forces so vast we can barely measure them, toward destinations we can't see, on paths we can't alter. Our motion through space isn't autonomous. We're not explorers charting our own course. We're debris caught in currents, flowing where gravity takes us. And the great attractor is hidden. We can infer its presence, calculate its mass, measure its effects, but we can't see it. The zone of avoidance blocks our view, our own galaxy's structure preventing us from observing the thing that's pulling us through space. Imagine that, something massive enough to drag thousands of galaxies through space, powerful enough to affect the motion of objects across hundreds of millions of light years, and we can't even see it directly. We can only see its shadow, the way galaxies around it move, the patterns in the cosmic structure, the gravitational fingerprints it leaves on everything nearby. There's a metaphor here, something about being pulled by forces you can't see, toward destinations you don't control. It's cosmic predetermination. We're on rails, following a path laid down by gravity billions of years ago, unable to deviate, unable to choose differently. Radio telescopes and infrared instruments can peer through the zone of avoidance to some degree, revealing glimpses of what's behind the obscuration. We've identified clusters of galaxies, massive concentrations of matter, regions of enhanced density, but the picture is incomplete. The full structure of the Great Attractor remains partially hidden, like looking at a map with missing sections. And maybe that's appropriate. Maybe it's fitting that the thing pulling us through space is hidden, mysterious, only partially understood. It makes the situation more unnerving. If we could see it clearly, understand it completely, maybe we'd feel more in control. But we can't. It's obscured. We're being pulled towards something we can't fully perceive. Some scientists have tried to calculate what would happen if we eventually reached the Great Attractor. Would the Milky Way merge with the galaxy clusters there? Would the gravitational interactions tear us apart? Would we simply pass through like water flowing past a rock in a stream? The answer is, it doesn't matter. The timescales are so long that none of this will occur before other cosmic events become relevant. The sun will die long before we reach the Great Attractor. The Milky Way and Andromeda will collide and merge. Cosmic expansion on larger scales will eventually overcome even the Great Attractor's gravity, pulling everything apart faster than gravity can draw it together. But in the meantime, we're moving, pulled by invisible forces, flowing through space like leaves in a river, unable to swim against the current, unable to choose our direction. And beyond the Great Attractor, there are other structures, other flows. The universe is networked with these gravitational currents, matter streaming along filaments of dark matter, pooling in clusters, creating a cosmic web of structure. We're one small part of that web, caught in currents that span the observable universe. It's humbling. We think of ourselves as important, as central, as significant, but cosmology reveals otherwise. We're not at the center of anything. We're not stationary. We're not even moving under our own power. We're being dragged through space by gravity, pulled by structures so massive they dwarf everything we know, flowing toward regions of space we may never reach. And there's no escape. You can't outrun gravity. You can't resist it. It's not a force you can shield against or deflect. It's the curvature of space-time itself. And if space-time is curved toward the Great Attractor, then everything in this region of space follows that curvature. We're passengers on a cosmic current, flowing towards something hidden, something massive, something we can't fully understand. And there's nothing we can do about it except observe, measure, try to understand the forces pulling us. The Great Attractor won't kill us. It won't destroy civilization. It's not a weapon or a threat in any immediate sense, but it's a reminder of our cosmic insignificance, of our powerlessness on large scales, of the fact that we're not in control of our trajectory through the universe. We're being pulled, always, constantly, by forces beyond our comprehension, toward destinations we can't see, on timescales longer than our species will exist. And the thing pulling us? It's hidden behind a curtain of dust and gas, invisible to direct observation, knowable only through its effects. That's the Great Attractor. Not a monster, not a threat, just a massive concentration of gravity, pulling everything nearby toward itself, indifferent to whether we want to go there or not. We're moving. We've always been moving. And we'll keep moving, pulled by invisible forces, until cosmic expansion or galactic collision or stellar death intervenes. Helpless, adrift, caught in currents we can't escape. That's not terrifying in the immediate sense, but it's unsettling in a deeper way, the realization that our motion through the universe isn't ours to control, that we're subject to forces vastly larger than ourselves, that the cosmos pulls us where it wills regardless of our desires. We're not exploring space. Space is moving us, and the great attractor is just one of the hands pushing us along. What do you think is pulling us? A concentration of dark matter? Something we haven't discovered yet? Or is the mystery itself the most unsettling part? What would you prefer, knowing what the great attractor is, or living with the mystery? Most matter in the universe is normal. Protons, neutrons, electrons arranged into atoms following rules we understand. Even the exotic stuff we've discussed, neutron stars, black holes, follows the laws of physics we've worked out. Extreme, yes, but comprehensible. But there's a hypothetical form of matter that's different, not just exotic, fundamentally strange. And if it exists, if even a tiny amount of it exists anywhere in the universe, it could be more dangerous than anything we've discussed so far. This is strange matter, and it might be contagious. Let me explain what strange matter is and why physicists are both fascinated and deeply concerned about it. Normal matter is made of up quarks and down quarks. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. These are the lightest quarks, and they're stable when bound together in these configurations. Everything you see around you, everything on Earth, everything in the solar system, is made from up and down quarks arranged into protons and neutrons. But there are other types of quarks. Strange quarks are heavier than up and down quarks, and normally they're unstable. They decay quickly into lighter quarks. You can create strange quarks in particle accelerators, but they don't last long. They exist briefly and then transform into the normal quarks we're familiar with. Maybe not always. There's a hypothesis in nuclear physics that under certain conditions, extreme pressure and density strange, quarks might become stable. Not individually, but when bound together with up and down quarks in specific configurations. This combination of quarks is called strange matter, and if it exists, it has a terrifying property. It might be more stable than normal matter. Think about what that means. If strange matter is more stable than normal matter, then any normal matter that touches strange matter might convert. The quarks and protons and neutrons would rearrange themselves into the strange matter configuration because it's lower energy, more stable. And once the conversion starts, it wouldn't stop. This is called the Ice-9 scenario, named after a fictional substance in Kurt Vonnegut's novel. In the book, Ice-9 is a form of water that's solid at room temperature, and any liquid water that touches it instantly freezes into more Ice-9. Strange matter would work the same way. Any normal matter touching it would convert into strange matter, releasing energy in the process. One speck of strange matter, smaller than an atom, touches normal matter. The conversion begins. The normal matter's quarks rearrange into the strange configuration. The newly formed strange matter touches more normal matter. That converts too. The process cascades, spreading through matter like a chain reaction, converting everything it touches into strange matter. If this happened to Earth, the planet would be converted in seconds. The strange matter would sink toward the core. Strange matter is denser than normal matter, converting everything along the way. Rock, metal, magma, all transforming into strange matter as the conversion wave spreads. Within hours, Earth would be reduced to a sphere of strange matter, smaller and denser than before, still orbiting the sun, but no longer a planet. Just a strange matter remnant, sterile and inert. And there would be nothing we could do to stop it. You can't contain strange matter. You can't isolate it. Any normal matter barrier would just convert when the strange matter touched it. The conversion is self-sustaining, potentially irreversible. Now, before you panic, this is hypothetical. We don't know if strange matter actually exists. We've never detected it. We've never created it in particle accelerators. It's a prediction of certain models of quark physics, but those models might be wrong. Strange matter might not be stable, after all. The conversion might not happen. But if it does exist, it could be out there, possibly created in the cores of neutron stars where densities and pressures are extreme enough that strange quarks might stabilize. These hypothetical objects are called strange stars, neutron stars that have converted, wholly or partially, into strange matter. And if strange stars exist, they might eject small fragments during starquakes or collisions. Tiny chunks of strange matter, called strangelets, hurled into space at high velocity. These strangelets would be incredibly small, maybe the size of a cell, maybe smaller but deadly. Any normal matter they encountered would convert. A strangelet traveling through the galaxy at a fraction of light speed, wandering for millions of years, could eventually pass through our solar system. If it happened to hit Earth, a low probability, but not impossible, the conversion would begin. Earth would start transforming into strange matter, and there would be no way to stop it. We'd have hours, maybe days, to realize what was happening. The conversion would release energy heat as matter rearranged into lower energy states. There might be seismic activity as the conversion wave spread through the planet. Strange matter is denser than normal matter, so as Earth converted, it would shrink. The surface would collapse inward. Oceans would drain into cracks opening in the crust. The planet would be geologically convulsing as it transformed. And then it would be over. Earth would be a strange matter sphere, maybe half its original diameter, orbiting the sun like nothing happened. The conversion would be complete. Everything that made Earth a planet, the rock, the water, the atmosphere, the life, all of it would be gone, transformed into strange quark matter. Humanity wouldn't survive, couldn't survive. We're made of normal matter. If Earth converts, we convert with it. Our bodies would be torn apart at the quark level, reorganized into strange matter configurations that bear no resemblance to biology, not death transformation into something that was never alive to begin with. And it wouldn't stop with Earth. Any space debris, satellites, spacecraft, anything in orbit made of normal matter would convert if the strange matter reached it. The conversion might even spread to other planets if fragments were ejected during Earth's transformation. A piece of strange matter Earth, launched into space during the collapse, could hit Mars or Venus, starting the conversion there. Eventually, the sun itself might be at risk. Strange matter is dense and might sink toward the sun's core if enough of it accumulated. The conversion of a star would be even more catastrophic than a planet, releasing enormous amounts of energy, possibly triggering a supernova-like explosion as the star's structure destabilized. This is the nightmare scenario. One strangelet, one tiny fragment of strange matter smaller than a cell, wandering the galaxy, hits Earth by chance, and everything ends. Not just humanity, everything. The planet itself transformed into something alien and dead. Is this likely? No. The odds of a strangelet hitting Earth are astronomically low. Space is vast. Strangelets, if they exist, are rare. The chances of one passing through our solar system, let alone hitting Earth specifically, are negligible. But they're not zero, and that's what makes this unsettling. We can't detect strangelets. We can't track them. We can't shield against them. If one is heading toward us, we wouldn't know until it arrived. And by then, it's too late. Some physicists have worried that particle accelerators might create strange matter. When we collide heavy ions at high energies, we create conditions similar to neutron star cores, high density, high pressure, extreme temperatures. Could we accidentally produce a strangelet in a collision? Probably not. The energies we reach in accelerators are lower than what occurs naturally in cosmic ray collisions. Cosmic rays high-energy particles from space hit Earth's atmosphere constantly, creating particle collisions far more energetic than anything we produce in laboratories. If cosmic rays haven't created strange matter and destroyed Earth over billions of years, our accelerators probably won't either. But probably isn't absolute certainty. There's a non-zero chance, however small, that a high-energy collision could produce a stable strangelet. That the next generation of particle accelerators could be the one that accidentally converts Earth into strange matter. It won't happen. The physics community has studied this extensively, and the consensus is that strange matter production in accelerators is impossible, or that strangelets, even if produced, wouldn't be stable outside the extreme conditions of their creation. But the worry existed, and it took careful analysis to rule it out. And even if we're safe from our own experiments, we can't rule out natural strangelets. If they exist, they're out there, produced in neutron star cores, ejected during collisions, wandering through the galaxy, invisible, undetectable, potentially catastrophic if one happened to intersect Earth's orbit. The probability is vanishingly low, but it's not zero, and that's enough to be unsettling. Strange matter is a reminder that our existence depends on the stability of normal matter. We assume protons and neutrons are stable, that atoms won't spontaneously rearrange, that the quarks making up everything we see will stay in their current configurations, and they will under normal conditions. But if strange matter exists, if there's a lower energy state for quarks to occupy, then normal matter is metastable. Not truly stable, just stable enough that conversion doesn't happen spontaneously, but it could be triggered by contact with strange matter, by the right conditions, and once triggered, the conversion would be irreversible. You can't turn strange matter back into normal matter. It's a one-way transformation, a terminal state. So we live with the possibility, remote but real, that somewhere in the universe there are fragments of strange matter drifting through space. And if one of them, by pure chance, happens to cross paths with Earth, that's the end. Not of humanity, of the planet, of everything. Converted, transformed, reduced to strange quark matter in a sphere orbiting the sun. All traces of what Earth was erased at the nuclear level. That's not a pleasant thought, but it's a possible thought, consistent with certain models of physics. And until we understand quark matter better, until we can definitively rule out stable strange matter, the possibility remains. A cosmic game of chance. Billions of years, and we've been lucky so far. No strangelet has hit us. Maybe none exist. Maybe we're safe. Or maybe one is out there right now, traveling through the galaxy, heading in our general direction. We wouldn't know, couldn't know. We'd just continue existing unaware until the moment strange matter made contact and the conversion began. And then we'd have hours to watch our planet die. Not from war or asteroid impact or climate change, but from transformation, from being converted into something no longer recognizable as Earth. Strange matter is the ultimate corruption, a substance that rewrites everything it touches, spreading through normal matter like a virus, converting it into something alien. And if it exists, if even a tiny amount exists anywhere in the universe, every planet is vulnerable. We're made of normal matter in a universe that might prefer strange matter. And if strange matter exists, our existence is contingent on never encountering it. That's not reassuring. That's just uncertainty, the kind of existential uncertainty that physicists prefer to rule out through experiments and calculations. But until we do, until we're sure strange matter either doesn't exist or isn't contagious, the possibility remains. A conversion wave spreading through Earth at the speed of sound in rock. Everything transforming, everyone dying. The planet shrinking, collapsing, becoming something no longer recognizable. All because a speck of strange matter, smaller than a cell, happened to hit us. If strange matter converted Earth, would you want to know it was happening? Or would ignorance be better? Think about it. Hours to watch the end or instant, unexpected transformation? Stars don't usually move fast. They orbit their galaxies at steady, predictable speeds, following gravitational paths that have been stable for billions of years. Our Sun, for instance, orbits the Milky Way's center at a pace that seems rapid by human standards, but is leisurely in cosmic terms. It takes hundreds of millions of years to complete one orbit, stable, predictable, safe. But there are stars that don't follow these rules. Stars moving so fast they're leaving the galaxy entirely. Stars accelerated to such extreme velocities that they've escaped the Milky Way's gravitational pull and are now hurtling through intergalactic space, never to return. These are hypervelocity stars, and if one passed through our solar system, it would be catastrophic. How does a star get moving that fast? What force is powerful enough to accelerate an entire star, an object with the mass of the Sun or greater to speeds high enough to escape a galaxy? The answer is supermassive black holes. At the center of most galaxies, including ours, there's a supermassive black hole, an object millions or billions of times more massive than the Sun. These aren't the stellar mass black holes formed from collapsed stars. These are gravitational monsters shaped by different processes, dominating the centers of galaxies with their immense gravity. Our galaxy's central black hole is relatively calm now, but it's surrounded by stars orbiting at incredible speeds. Stars that venture too close to the black hole move faster and faster as they're caught in tighter and tighter orbits, whipping around the black hole in trajectories that would be impossible anywhere else. Sometimes a binary star system, two stars orbiting each other, wanders too close to the supermassive black hole. The black hole's gravity is so strong that it can tear the binary apart. One star gets captured, falling toward the black hole, eventually being consumed. The other star gets flung away, accelerated by the gravitational slingshot effect to enormous speeds. Imagine a slingshot on cosmic scales. The star that gets ejected doesn't just leave the galactic center, it leaves the galaxy entirely, accelerated to speeds fast enough to overcome the Milky Way's gravity. It shoots out into intergalactic space, a rogue star traveling through the void between galaxies. We've detected these hypervelocity stars. Not many, they're rare, and they're difficult to spot because they're moving so fast they don't stay in any one region of the sky for long. But we found enough to confirm the phenomenon is real. Stars ejected from galactic centers, traveling at speeds measured in hundreds of kilometers per second, fast enough to cross the galaxy in millions of years, rather than hundreds of millions. And here's the nightmare scenario. What if one of these stars is heading toward us? A hypervelocity star wouldn't hit the sun. Space is vast, and the odds of a direct collision are essentially zero. But it doesn't need to hit. Gravitational interactions alone would be enough to cause catastrophe. If a hypervelocity star passed through our solar system, even at a distance of several light years, its gravity would perturb everything. The Oort cloud, that vast sphere of comets surrounding our solar system at its outermost edge, would be disrupted. Thousands of comets would be knocked from their stable orbits, sent falling toward the inner solar system. We'd see them coming. Comets don't move at light speed, so there would be years or decades of warning as the swarm approached. But warning doesn't mean we could stop them. We don't have the technology to deflect thousands of comets simultaneously. We'd be helpless as they rained into the inner solar system, some hitting planets, some passing close enough to cause gravitational chaos. And that's if the hypervelocity star stays distant. If it passed closer within a light year within the Oort cloud's inner edge, the effects would be more severe. The outer planets would feel the gravitational tug. Their orbits would shift, becoming more elliptical, more chaotic. Neptune, Uranus, Saturn, all of them would experience orbital perturbations. These changes would be slight at first, but over time, they'd compound. The solar system's architecture, stable for billions of years, would begin to destabilize. And if the star came even closer, if it passed through the inner solar system, closer than the orbit of Jupiter, the chaos would be immediate and devastating. Earth's orbit would change. Not drastically, a passing star wouldn't fling Earth into the sun or out of the solar system in one encounter. But even small changes to Earth's orbit are catastrophic for life. A slightly more elliptical orbit means more extreme seasons, longer summers, harsher winters, climate zones shifting, ecosystems collapsing, or worse, the orbital plane could tilt. Earth's axis is already tilted relative to its orbit, which is why we have seasons. But the orbital plane itself could tilt relative to the sun's equator, creating even more complex climate variations. Regions that were temperate might become uninhabitable. Ice ages could trigger in areas that were previously warm. The moon's orbit would destabilize. The moon stabilizes Earth's axial tilt, keeping our climate relatively consistent. If the moon's orbit changed significantly, if the gravitational interaction with the passing star pulled it into a more elliptical orbit or altered its orbital plane, Earth's axial tilt would start varying chaotically. Seasons would become unpredictable. Long-term climate stability would be lost. And it's not just Earth. Every planet would be affected. Mars, already cold and marginal for potential future colonization, could be pulled into an orbit that makes it even more hostile. Venus could move closer to the sun or farther away. Mercury might be ejected from the solar system entirely, flung outward by the gravitational chaos. The asteroid belt would be particularly vulnerable. Those rocks are held in place by a delicate balance between the Sun's gravity and Jupiter's gravitational influence. A passing star would disrupt that balance, scattering asteroids in all directions. Some would fall toward the Sun, passing through the inner solar system, creating an impact hazard that would last for millennia. Jupiter itself, the solar system's guardian that normally deflects comets and asteroids away from Earth, might have its orbit altered enough that it no longer provides that protection. Or worse, Jupiter's altered orbit might send more asteroids toward the inner planets instead of deflecting them away. The timescale for these effects would vary. Some changes would be immediate. Comets knocked loose during the encounter would start falling inward within years. Other effects would take longer orbital changes, accumulating over decades or centuries, gradually destabilizing the system, making it less habitable, less predictable, less safe. And here's what makes hypervelocity stars particularly terrifying. We might not see them coming. These stars are moving fast, and they're not necessarily bright. If a hypervelocity star is a red dwarf, a small, dim star, it could approach within a few light years before we noticed it. By the time we detected it, it might be too close to avoid the gravitational effects. We'd have warning, yes, but not enough time to do anything except watch as it passed through our neighborhood and disrupted everything. Could we deflect it? No. Could we shield Earth from its gravitational influence? No. Gravity penetrates everything. There's no defense except distance, and if the star is already close, distance isn't an option. The best we could do is prepare for the consequences, evacuate regions likely to be hit by comets, build underground shelters to survive impacts, stockpile food for the years when climate disruption makes agriculture impossible, plan for a world where the stable climate and predictable seasons we've relied on for all of human history are gone, replaced by chaos. How common are hypervelocity stars? Not very, thankfully. The process that creates them, binary stars disrupted by supermassive black holes, doesn't happen often. Most binary systems never get close enough to galactic centers to be torn apart. And even when they do, the ejected star has to be moving in the right direction to head toward us specifically. We've detected a few dozen hypervelocity stars in our galaxy, but most of them are far away, moving in directions that won't bring them near our solar system. The odds of one passing close enough to cause problems are low, but they're not zero. And in a galaxy with hundreds of billions of stars, even low probabilities add up over time. Over millions of years, over billions of years, the odds shift. Eventually, a hypervelocity star will pass close enough to matter. Maybe not in our lifetimes, maybe not for thousands of generations, but eventually, and when it happens, we'll have to deal with the consequences: a solar system in chaos, orbits disrupted, climates destabilized, a cascade of changes that make Earth less habitable and the solar system less safe. Hypervelocity stars are cosmic proof that stability is temporary. Our solar system seems permanent, unchanging, reliable, but it's only stable because nothing has disturbed it. A passing star, even one that doesn't hit anything, that just passes through, would be enough to destabilize everything. And we can't prevent it, can't deflect a star, can't shield against its gravity, can't do anything except hope we're not in any hypervelocity star's path, hope that the galaxy's geometry keeps these ejected stars far away from us. Hope That's all we have. Hope and the vast emptiness of space that keeps most threats distant. But the galaxy is old, and hypervelocity stars have been flying through it for billions of years. Some must have passed through our neighborhood already, in the distant past, before Earth existed or before life evolved. Some must have disrupted other solar systems, destabilizing planets, causing extinctions on worlds we'll never know about. And some are traveling toward us right now, maybe distant, maybe centuries or millennia away, maybe close, approaching from a direction we haven't looked carefully enough. We won't know until they arrive, until we detect the fast-moving star, calculate its trajectory, realize it's going to pass close. And then we'll have years or decades to prepare, not to stop it, not to avoid it, but to brace for impact. Not physical impact, gravitational impact. The invisible violence of a massive object moving too fast, pulling on everything nearby, disrupting orbits, scattering comets, destabilizing the delicate architecture that makes life possible. Hypervelocity stars are wanderers, exiles from galactic centers flung into the void by black holes traveling through space forever. They're not hunting us. They're not even aware of us. They're just moving, following ballistic trajectories through the galaxy. And if we happen to be in their path, we'll feel the consequences. No malice, no intention, just bad luck and bad timing. That's how the universe works. It doesn't target you. It just moves, and if you're in the way, you suffer the consequences. Hypervelocity stars are out there, moving, approaching, and we can only hope none of them are heading our way. If we detected a hypervelocity star approaching our solar system, would you want to be told? Would you want years of warning, or would you rather live in ignorance until the effects became obvious? What would you do with that knowledge? The universe is mostly empty. You know this intellectually. Space is vast. Stars are separated by light years, galaxies by millions of light years. Emptiness is the norm. Matter is the exception. But there are regions of space where empty takes on a new meaning. Places where the emptiness is so complete, so absolute, so vast that calling them empty feels inadequate. These are the cosmic voids, and they're more disturbing than you might think. Imagine looking up at the night sky and seeing nothing. Not darkness with stars scattered through it, just darkness. Pure, featureless black in every direction, extending as far as telescopes can see. No galaxies, no stars. No nebulae or clusters or any indication that the universe contains matter at all. Just void. This is what you'd see from inside a cosmic void. And these voids are enormous hundreds of millions of light years across. Regions of space so empty that if you were somehow transported to their centers, the nearest galaxy might be farther away than our entire observable universe was when it was young. How do these voids form? Why is the universe structured this way, with matter concentrated in filaments and clusters, leaving vast bubbles of near emptiness in between? The answer goes back to the early universe, to tiny quantum fluctuations in the first moments after the Big Bang. These fluctuations created slight variations in density, some regions slightly denser, others slightly less dense. Gravity amplified these differences. Dense regions attracted more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming emptier. Over billions of years, this process created structure. Matter flowed along gravitational gradients, pooling in filaments and nodes, draining from the regions between. The result is a cosmic web-dense filaments of galaxies surrounding vast, empty voids, and these voids are growing. As the universe expands, the voids expand with it, becoming larger and emptier. Dark energy, the force driving cosmic expansion, might be stronger in voids where there's less matter to resist it. The voids could be expanding faster than the universe's average expansion rate, growing like bubbles in expanding foam. Galaxies near void edges are being pulled away from the voids toward denser regions. The voids are clearing out, becoming more empty, more isolated. Anything inside a void is becoming more alone as expansion carries away even the distant galaxies that were once visible on the horizon. Now imagine being in a civilization inside a cosmic void. Not impossible, there might be a few isolated galaxies in even the emptiest voids, orphaned during the universe's early structure formation. If intelligent life arose in one of these galaxies, what would their astronomy look like? They'd look out at the universe and see almost nothing. A few nearby galaxies, perhaps, if they were lucky. But beyond that, just darkness. No cosmic web. No distant galaxy clusters. No visible universe beyond their local neighborhood. They might develop science, discover physics, realize the universe is expanding, but they'd have no evidence of the larger structure. No way to know that beyond their local group, beyond the empty horizon, there are billions of galaxies arranged in vast filaments and superclusters. They'd be functionally alone in an observable universe that appears empty, not because it is empty, but because they're in a region where matter is absent and the nearest concentrations are too far away to see. This is cosmological isolation. Being in a universe that contains structure and richness, but being positioned such that none of it is accessible, none of it is visible. It's like being on an island in an ocean so vast that no other land is visible, no hint of other continents, no evidence that anything exists beyond the water surrounding you. And here's the disturbing part. We might be heading toward a void. The Milky Way is currently in a relatively dense region part of the cosmic web's structure, surrounded by other galaxies, visible superclusters in many directions. But the universe is expanding, structure is evolving, and cosmic flows are moving galaxies along the web's filaments. Some models suggest our local group, the Milky Way, Andromeda, and the smaller galaxies gravitationally bound to us, might be moving toward a void edge. Not falling into the void, but being carried by cosmic flows along its boundary. Over billions of years, as expansion continues, we might find ourselves in an increasingly empty region of space. Future civilizations, billions of years from now, might look out at the universe and see fewer galaxies than we see today. Not because galaxies are dying, but because they're receding, carried away by expansion, crossing beyond our cosmic horizon. The universe would appear to be emptying, becoming more void-like, more isolated. And it gets worse. Dark energy is accelerating expansion. Galaxies beyond our local group are receding faster and faster, approaching and eventually exceeding the speed of light relative to us. Not because they're moving through space faster than light, that's impossible, but because space itself is expanding, and the expansion adds up over distance. Eventually, distant galaxies will recede so fast that their light can never reach us. They'll cross our cosmic horizon, disappearing from view, never to be seen again. Our observable universe will shrink, not because we're losing the ability to see, but because there will be less to see. Galaxies slipping away one by one as expansion carries them beyond reach. In trillions of years, observers in the Milky Way might see nothing beyond our local group. All other galaxies will have receded beyond the horizon. The universe will appear to contain only a few galaxies, ours, Andromeda, and whatever smaller galaxies remain gravitationally bound. It'll look like we're in a cosmic void, isolated, alone. Even though billions of galaxies exist beyond the horizon, they'll be invisible, unreachable, forever separated from us by expansion. This is the future isolation awaits, not because the universe is emptying, but because expansion is separating us from everything beyond our local group. We're not entering a void, we're creating one, or rather expansion is creating one around us, cutting us off from the larger cosmos. And there's nothing we can do about it. We can't stop expansion, can't slow dark energy, can't prevent distant galaxies from receding beyond our reach. We can only watch as the universe becomes more empty from our perspective, as the observable cosmos shrinks, as we're left increasingly alone. Some astronomers worry about future civilizations. If humanity or our descendants survive for billions of years, what will their cosmology look like? They'll observe only a handful of nearby galaxies, all gravitationally bound. They might never discover the expanding universe because there won't be distant galaxies receding to measure expansion against. They might conclude the universe consists only of their local group, that nothing exists beyond the darkness surrounding them, that they're alone, not in the sense that no other life exists, but in the sense that the entire cosmos is just a few galaxies in an infinite void. They'd be wrong, but they'd have no way to know. The evidence, distant galaxies, cosmic expansion, the microwave background, would be gone, lost to expansion, carried beyond the horizon before their civilization arose. This is informational isolation, living in a universe rich with structure but being unable to see it, unable to detect it, unable to prove it exists. It's like being blind and trying to understand color. The phenomenon exists, but you're cut off from the evidence needed to discover it. And it's not just future civilizations. We might be in that situation now in a different way. The cosmic voids we observe, how do we know they're truly empty? Maybe they contain things we can't detect. Dark matter, sure, but maybe something else. Maybe structures or objects that don't emit light, don't interact electromagnetically, exist in the voids but remain invisible. We map the voids by observing where galaxies aren't. Absence of light equals emptiness. But absence of evidence isn't evidence of absence. The voids might not be as empty as they appear. There could be things there, dark structures, invisible objects, phenomena we haven't imagined, and we'd never know because we're looking for light and finding none. The voids are defined by absence. No galaxies, no stars, no visible matter. But absence is unsettling. It's the space between things, the gaps in the cosmic structure, the regions where nothing we can detect exists. And humans don't handle absence well. We fill voids with imagination, with speculation, with worry about what might be hidden there. Maybe the voids are truly empty. Maybe they're just regions where matter didn't accumulate, where gravity didn't pull things together, where the universe's structure left gaps. That's probably true. That's what the evidence suggests. But maybe not. Maybe there's something in the voids we haven't found yet. Something that doesn't emit light, doesn't clump like normal matter, doesn't interact with anything we can detect. Something invisible filling the apparent emptiness existing in the gaps. Probably not. Almost certainly not. But the voids are so vast, so empty, so unlike the regions where matter concentrates that they feel wrong, unnatural. Like the universe forgot to put anything there, or like something removed what was there, leaving only absence. This is the horror of emptiness. Not the crowded horror of black holes or magnetars or gamma-ray bursts. Just nothing. Vast regions of space where nothing exists for distances that dwarf galaxies, where you could travel for millions of years at the speed of light and never encounter anything. If you were in a void truly in its center, you'd see darkness in all directions. Not the friendly darkness of night with stars overhead, but absolute darkness. The void's edges would be so far away that even the galaxies clustered there would be too distant to see clearly. Just faint fuzzy blobs of light impossibly far away, isolated points in an ocean of black. You'd be more alone than anyone has ever been. Not alone in the sense of no other people, but alone in the sense of no other matter. No planets, no stars, no galaxies near enough to see details. Just you and the emptiness and the knowledge that the nearest galaxy is farther away than anything humans have ever observed. That's cosmological horror. Not being destroyed, not being hurt, just being isolated so completely that you're cut off from everything, floating in a void so vast that help couldn't reach you even if it traveled at light speed for millions of years. The voids are growing, expanding, becoming more empty as the universe ages and expansion accelerates. Regions that currently have a few sparse galaxies will lose even those as expansion carries them away. The voids will consume more space, become larger, more empty, more isolating. And we're somewhere on the structure, surrounded by voids, bordered by emptiness. We're in a dense region now, but we're also aware that most of the universe's volume is void. Most of space is empty. We're the exception, living in a region where matter concentrated, looking out at a universe that's mostly nothing. The voids are patient. They don't need to do anything. They just exist, growing slowly, waiting for expansion to carry matter away from their edges, waiting to become even emptier than they already are. In the end, if dark energy continues accelerating expansion, the entire universe might become void-like. Galaxies separated by such vast distances that each appears alone, isolated, surrounded by emptiness. The cosmic web dissolving, structure dispersing, everything drifting apart until there's nothing but isolated islands of matter in an infinite ocean of void. That's the future. Not heat death exactly, but something similar cosmological isolation where everything exists but nothing is connected, where matter persists but is so separated that interaction becomes impossible. The voids win, eventually, given enough time. Expansion carries everything away, and what remains is emptiness. We're not there yet. We're still in the era where galaxies cluster, where structure exists, where the universe is comprehensible. But the voids are there, waiting, growing, patient, and someday they'll be all that's left. Would you rather be trapped in a cosmic void where you could see nothing, or near a black hole where you'd at least see matter being destroyed? Which isolation is worse, emptiness or chaos? Think about it. Everything we've discussed so far, rogue black holes, gamma ray bursts, vacuum decay, these are threats that might happen, possibilities, things that could end us but might not, disasters we might avoid through luck or timing or the sheer vastness of space keeping dangers distant. What I'm about to describe is different. This isn't a possibility, it's a certainty. Not something that might happen, but something that will happen, guaranteed, inevitable, written into the fundamental laws of physics. The universe is dying, slowly, inexorably, and there's nothing anyone can do to stop it. This is heat death, and it's the ultimate fate of everything that exists. Let me explain what heat death is, and why it's worse than any catastrophe we've discussed so far. The second law of thermodynamics states that entropy, disorder, randomness, the dissipation of useful energy always increases in a closed system. You can decrease entropy locally by expending energy, by organizing things, by creating order. But the total entropy of the system always goes up. You can't reverse it. You can't reset it. You can only watch as everything gradually becomes more disordered, more random, more useless. The universe is a closed system. There's nothing outside it to inject energy, nothing to reverse the entropy increase. So the universe's total entropy is rising, has been rising since the Big Bang, will continue rising forever, and eventually, inevitably, the universe will reach maximum entropy, the point where no more disorder is possible, because everything is already as disordered as it can be. No energy gradients remain. No temperature differences exist. No useful energy is available to drive any process whatsoever. This is heat death, the end state, the final configuration. Not dramatic, not violent, just nothing, forever. Here's how it happens. Right now, the universe contains energy gradients. Stars are hot, space is cold. This temperature difference allows energy to flow, allows processes to occur, allows complexity and structure to exist. Life depends on these gradients. Every living thing extracts energy from its environment by exploiting temperature differences or chemical potential differences. But these gradients are temporary. Stars burn fuel, converting hydrogen into helium and heavier elements, releasing energy as heat and light. This energy radiates into space, warming the cold void. Very slowly, very gradually, the temperature difference between stars and space decreases. Eventually, every star will burn out. Not might burn out, will burn out. Stars have finite fuel. Even the longest-lived red dwarfs, which can burn for trillions of years, will eventually exhaust their hydrogen. The last stars in the universe will die, winking out one by one, leaving behind cooling remnants, white dwarfs, neutron stars, black holes. And then the universe will be dark. No more stars, no more fusion, no more light. Just darkness, cooling remnants, and the expansion of space carrying everything farther apart. But it doesn't end there. Black holes persist, but even they're not eternal. Stephen Hawking discovered that black holes emit radiation through quantum effects near their event horizons, slowly, incredibly slowly. A stellar mass black hole takes far longer than the current age of the universe to evaporate completely, but eventually it will. Every black hole will eventually radiate away all its mass, disappearing in a final burst of radiation. The supermassive black holes at galactic centers, billions of times the sun's mass, will take unimaginable timescales to evaporate. Timescales so long that writing them in years is meaningless, but they will evaporate. Given enough time, Hawking radiation will reduce even the largest black holes to nothing. And then there's nothing left that can generate energy. No stars, no black holes, no fusion, no accretion. No processes that create order or complexity. Just particles, photons, neutrinos, maybe a few stable particles if protons don't decay, spreading through an ever-expanding void. The temperature approaches absolute zero. Not reaches, approaches. As the universe expands, the cosmic microwave background radiation cools. Its photons stretch to longer and longer wavelengths. Eventually, the temperature becomes so low that thermal energy is negligible. Everything is cold, uniformly cold. No hot spots, no warm regions, no temperature differences whatsoever. At this point, entropy is maximized. The universe has reached equilibrium, and in equilibrium, nothing happens. Can't happen. All processes require energy gradients, require the ability to extract useful work from differences in energy or temperature or chemical potential. But in a maximum entropy state, no gradients exist. Everything is uniform. Everything is still. This is heat death. Not heat in the sense of warmth, but heat in the thermodynamic sense, the dissipation of energy into unusable forms, the death of useful energy, of gradients, of the ability to do work or drive change. And it's permanent. You can't reverse entropy increase without expending energy from an external source. But the universe is the only system. There is no external source. Once maximum entropy is reached, the universe stays there forever. What does this look like? What would you experience in a heat-death universe? Nothing, because you couldn't exist. Life requires metabolism, which requires energy flow, which requires gradients. In a maximum entropy universe, no gradients exist. No energy flows. Metabolism is impossible. Life in any form we can imagine cannot exist. But imagine you could somehow observe this universe from outside, immune to its physical laws. What would you see? Darkness. Absolute darkness. No stars, no galaxies, no glowing gas clouds. The universe would be completely dark because there are no energy sources to emit light. Cold. Temperatures approaching absolute zero. No warmth anywhere. No heat radiation. Just the faint, stretched-out remnants of the cosmic microwave background, cooled to temperatures barely above the theoretical minimum. Stillness. No motion except perhaps quantum fluctuations. Particles would exist, scattered through infinite space, but they wouldn't interact meaningfully. No collisions, no reactions, no processes. Just isolated particles drifting through void. Silence. Not that sound could propagate any way. There's no medium, no atmosphere. But even metaphorically, the universe would be silent. No events occur. Nothing changes. There's no story to tell because nothing is happening. Time becomes meaningless. We measure time by change, by events occurring in sequence. But in a maximum entropy universe, nothing changes. One moment is identical to every other moment. Time still exists. Technically, space-time is still there, but there's no way to measure it, no way to perceive its passage. It becomes an abstract concept rather than an experienced reality. This is the heat-death state, not non-existence, because the universe still exists, just stasis, eternal, unchanging, meaningless stasis, forever, and there's no escape. No clever trick will save us. No technology will prevent this. The laws of thermodynamics aren't suggestions, they're absolute. Entropy increases, always, eventually reaching maximum, inevitably. Some physicists have speculated about ways to survive heat death or postpone it. Maybe civilizations could harvest energy from black hole evaporation, surviving until the very last black holes disappear. Maybe intelligence could transition to forms that require less energy, existing in colder and colder conditions as the universe cools. But these are just delays, postponements. Eventually, even the last black hole evaporates. Eventually, even the most efficient information processing requires energy that isn't available. Eventually, everything ends, unless protons decay. Some theories predict that protons aren't stable forever, that they eventually decay into lighter particles. If this is true, then even the particles making up matter will eventually disappear, breaking down into radiation and decay products that spread through the void. This accelerates heat death, in a sense. If protons decay, then within an incomprehensible but finite timescale, maybe 10 to the power of 34 years, all atomic nuclei will have decayed. No more atoms, no more matter as we know it. Just radiation and exotic particles spreading through infinite space. Either way, whether protons decay or remain stable, the end state is the same. Maximum entropy, uniform temperature, no energy gradients, no processes, no change, nothing. This is what the universe is heading toward. Not in billions of years, not in trillions, but in timescales so vast that they dwarf all other cosmic timescales. The current age of the universe, roughly 14 billion years, is nothing compared to the time remaining until heat death. Literally nothing. A rounding error. An instant. The universe is young, incredibly young. We're living in what might be called the first moments of cosmic history, the brief period when stars still shine, when energy is available, when complexity is possible. This is the age of light, of heat, of structure. It won't last. Most of the universe's existence, most of its future, will be spent in the heat-death state. Dark, cold, still eternal. The age of light is a brief flicker at the beginning, an anomaly, a temporary deviation from the long equilibrium that awaits. And there's something profoundly depressing about this. Everything we do, everything we build, everything we achieve, all of it is temporary. Not just temporary in human terms, but temporary in cosmic terms. Eventually it all ends. Not destroyed by catastrophe, not erased by violence, but simply dissolved by entropy, dissipated by the relentless increase in disorder. Stars will fade, galaxies will disperse, black holes will evaporate, and in the end, nothing will remain except darkness and cold and the uniform distribution of particles through infinite space. No memory of what came before, no trace of civilizations or consciousness or complexity. Just void. This isn't hypothetical. This isn't speculation. This is what thermodynamics predicts with the same certainty that it predicts ice melts and hot coffee cools. Entropy increases, always, until maximum entropy is reached, and then nothing more happens, ever. Some find this comforting in a strange way. If everything ends anyway, if the ultimate fate is the same regardless of what happens, then maybe the details don't matter. Maybe the journey is all we have, and knowing it ends shouldn't diminish the experience of living it. Others find it horrifying. If everything is temporary, if nothing ultimately matters because entropy will erase it all, then what's the point? Why build, why create, why care if it's all heading toward the same cold ending? There's no good answer to that question. It's philosophical, not scientific. But the science is clear. Heat death is coming, inevitable, certain. The universe has an expiration date written into its fundamental laws. We won't experience it. Humanity will be long gone before heat death arrives. The sun will die in several billion years. The Milky Way will collide with Andromeda. Earth will be destroyed or ejected, and our species will either have evolved beyond recognition or gone extinct. But the universe will still be here, still expanding, still increasing in entropy, still moving toward that final state where nothing more can happen. And when it arrives, in time frames so vast they're meaningless, the universe will settle into its eternal equilibrium. Dark, cold, still, forever. No more stars, no more life, no more events. Just the universe existing in its final state, unchanging and unchangeable for the rest of eternity. That's not a threat you can fight. That's not a danger you can avoid. That's just the end, guaranteed and absolute, waiting patiently at the end of all time. Heat death is the universe's final answer, not dramatic, not violent, just inevitable. Everything ends in darkness and cold, everything, always, and there's nothing anyone can do about it except accept it and make the most of the brief, bright age we're living in, the age before the darkness, before the cold, before the final silence, because this age won't last. Nothing lasts. Entropy ensures it. Welcome to thermodynamics. Welcome to reality. Welcome to the knowledge that the universe has a final state, and that state is nothing, forever. Knowing the universe will end this way, does it make current existence more or less meaningful? Does inevitable doom make life precious or pointless? What do you think? So here we are. We've traveled through the universe's catalog of horrors. Rogue black holes wandering invisibly through the galaxy. Gamma-ray bursts sterilizing planets from across light years. Vacuum decay bubbles that could erase reality itself at light speed. Magnetars with magnetic fields strong enough to kill from the moon's distance. The great attractor pulling us toward something we can't see. Strange matter that converts everything it touches. Hypervelocity stars disrupting solar systems. Cosmic voids that isolate civilizations in oceans of emptiness. And heat death, the guaranteed end of everything, written into the laws of physics themselves. These aren't fantasies. These aren't science fiction nightmares. These are real phenomena, confirmed by observation or predicted by our most reliable theories. The universe contains things that can kill you in ways you never imagined, on scales you can barely comprehend, through mechanisms that make human violence look quaint. And yet here we are, still alive, still existing, still looking up at the stars and wondering. That's remarkable when you think about it. Given everything the universe can do, given all the ways existence can end, all the threats wandering through space, all the instabilities waiting to manifest, the fact that we're here at all is almost miraculous. Not actually miraculous, there's no divine intervention protecting us, just statistical. We're here because we've been lucky, because none of these cosmic catastrophes have happened to us yet. But luck has gotten us this far. We exist in a brief window of cosmic time when the universe is old enough to have formed complex structures, but young enough that stars still shine. We exist on a planet in a stable orbit around a stable star, far from galactic hazards, shielded by atmosphere and magnetic fields, protected by Jupiter's gravity, deflecting most asteroids. We're in a Goldilocks situation on every scale. The right planet, the right star, the right location in the galaxy, the right epoch in cosmic history. Change any of these factors, and we wouldn't exist. We're the product of countless fortunate accidents, unlikely configurations, threats that happened to miss. And knowing this, knowing how precarious existence is, how many ways it can end, how temporary our cosmic moment is, what should we do? Some would say it means nothing matters. If vacuum decay could erase us tomorrow, if heat death is inevitable billions of years hence, if we're just temporary patterns in a universe that doesn't care, then why try? Why build? Why care about anything? But that's backwards. The fragility of existence is exactly what makes it precious. We're not guaranteed tomorrow. We're not promised safety. We exist now in this moment, and that's all we have. The universe won't last forever, but it's lasting now. Stars won't shine eternally, but they're shining today. Life won't persist until heat death, but it's here, experiencing aware thinking. That matters. Not in a cosmic sense. The universe doesn't assign meaning or value, but to us it matters. We're the ones who experience existence. We're the ones who appreciate beauty, who create complexity, who look at the cosmos and understand what we're seeing. The universe is terrifying, absolutely, objectively, undeniably. It contains more ways to die than we can imagine, more threats than we can defend against, more scales of violence than our minds can comfortably hold. But it's also beautiful. The same processes that create gamma-ray bursts also create heavy elements, seeding space with the materials for planets and life. The same gravity that could pull us toward black holes also holds planets in stable orbits and galaxies in clusters. The same entropy that will eventually lead to heat death is currently allowing stars to shine, driving the processes that make complexity possible. Terror and beauty aren't opposites in the cosmos. They're intertwined. The universe is dangerous because it's powerful, and that power is what makes everything interesting, everything possible, everything real. We're afraid of rogue black holes, but black holes are also fascinating objects so extreme that they warp space-time, creating conditions unlike anywhere else. We're disturbed by vacuum decay, but the fact that reality itself might be metastable tells us something profound about the nature of existence. We're unsettled by cosmic voids, but those voids are part of the large-scale structure that makes the universe comprehensible, that creates patterns we can study and understand. Every horror is also a discovery. Every threat is also a window into physics. Every way the universe can kill us is also a way we learn what the universe is. And maybe that's the point. Not that there's no danger, there's immense danger everywhere, always, but that despite the danger, despite the precariousness, despite knowing how temporary and vulnerable we are, we're still here, still curious, still trying to understand. Humanity has always been aware of death, personal death, inevitable and certain, but we build civilizations anyway. We create art. We pursue knowledge. We love and connect and strive, knowing none of it is permanent, knowing everything ends. Cosmic threats are just death on a larger scale. The principles are the same. Acknowledge the danger, accept the impermanence, and live anyway, because the alternative is giving up before we've even started. The universe is hostile, but it's also where we live. It's the only place we can live. Complaining about cosmic threats is like complaining about the weather. Valid, understandable, but ultimately pointless. The universe doesn't care. It just is, and we're part of it, subject to its laws, vulnerable to its violence, but also capable of understanding it. That's the miracle, if there is one. Not that we're safe, we're not. Not that we're protected, we aren't, but that we're aware. We can look at the universe, recognize the threats, understand the physics, and keep living anyway. Keep exploring. Keep learning. Keep appreciating the brief moment of complexity and consciousness we've been given. The rogue black holes are still out there. The gamma-ray bursts can still happen. Vacuum decay might occur tomorrow. Heat death is still inevitable. Nothing has changed except our awareness of these threats. But awareness isn't worthless. Understanding the universe, really understanding it in all its terror and majesty, is perhaps the most human thing we do. We're the universe experiencing itself, matter organized into patterns, capable of recognizing other patterns, consciousness arising from physics and chemistry and chance. And if that consciousness exists, knowing it's temporary, knowing it's vulnerable, knowing the universe contains horrors beyond measure, that doesn't diminish it. That's just honest. That's reality without illusion, so we continue. Not because we're guaranteed survival, not because we're protected from cosmic threats, not because everything will be fine. We continue because we're here, now, in this moment, and that's enough. The universe is terrifying, but it's also home, and we're not done exploring it yet.